Hello, today we're continuing with our GCSE Physics Revision series looking at nuclear fission. We've already said that decay happens when atoms are unstable and they decay by the emission of radioactive rays, alpha, beta and gamma. Well, nuclear fission happens when you have a very large nucleus, something like, say, uranium, and that splits into two smaller nuclei. It's rather like a liquid drop. If a liquid drop gets too big, then it splits up into two smaller blobs. And that's exactly what happens with a very large atom. It splits into two smaller sections. And those, of course, are two new atoms. And what happens in nuclear fission? There are many ways of doing it, but one example, for example, is to take the element uranium and you hit it with what's called a thermal neutron, which basically means it's a slow-moving neutron. And that will cause the uranium atom to split into two smaller atoms. There are many atoms it could split into, but in this particular case, I'm going to have it splitting into a barium atom and a krypton atom. But it also produces three other neutrons. So a neutron hitting a uranium atom produces two smaller atoms, barium and krypton, but it also kicks out three individual neutrons. Now, obviously, those individual neutrons can now go on and hit three more uranium atoms, and each time they hit an atom, that will split that atom into barium and krypton and three more neutrons. And so it goes on. So one neutron hitting a uranium atom produces two smaller atoms and three neutrons. Those three neutrons can then hit three uranium atoms, producing smaller atoms and three more neutrons. But there's something else you get out of this process. So let me write out the full equation of what is actually happening. We start with uranium, which of course has 92 protons, and in this particular case it has 235 protons plus neutrons. It's called uranium-235. We add to that the thermal neutron, which of course has no protons and one neutron. And that, we said, produces barium, which has 56 protons and 141 protons plus neutrons, plus krypton, which has 36 protons and 92 protons and neutrons, plus three, we said, neutrons, which of course have no protons, one neutron. But you also get something else, and that something else is energy. And that energy is typically given off in the form of heat or light. I pause at this point just to point out that, as with the previous video, these equations have to balance. The numbers at the top have to balance, the numbers at the bottom have to balance. Let's just check. On this side we've got 235 plus 1 is 236. On the top we've got 141 plus 92 plus 3 lots of 1 comes to 236. Similarly, on the bottom we've got 92 plus 0 is 92. And on this side we've got 56 plus 36 plus 0 is 92. Where does this energy come from? Well, if you could take the uranium and the neutron and put them on a scale, and you could take the barium and the krypton and the three neutrons and put those on a scale, what you would find is that the one atom of uranium and the neutron would be heavier than the one atom of barium, the one atom of krypton and the three neutrons. there's a slightly greater mass than there is here. In other words, when this atom and the neutron decay into these 2 atoms and 3 neutrons, there's what's called a mass deficit. Some of the mass disappears. Where on earth does that mass go? Well, you've probably all heard of Einstein's famous equation, E equals mc squared. Energy is mass times the speed of light squared. And what has happened is that that mass deficit has been converted into energy. That's this energy here. Now it's a very, very small mass deficit. But look, whatever mass you have, you multiply by c squared. C is the speed of light. It's 3 times 10 to the 8th meters per second. So c squared is a massive number. It's 9 times 10 to the 16. So even if you have a very, very small mass deficit, you multiply it by a very, very large number and you get a lot of energy. And that's just from one atom. But remember, every decay produces 3 neutrons. And each one of those neutrons can hit another uranium atom and produce still more neutrons. And that will just build up and it becomes a chain reaction. And every time the atoms split, you get more and more and more and more energy. And that is the basis of an atomic bomb. You have uranium, you effectively have neutrons that start the process going. Once the process is going, it's unstoppable because it's just producing 3 neutrons for every decay, so 3 more atoms can be hit. This produces an absolutely gargantuan amount of energy, which is the explosion that you see in an atomic bomb. I'll give you the formula for another version here. If you take plutonium, which has 94 protons, and here we're going to use plutonium-239, and we send in our thermal neutron, that will become, in this case, we've got strontium, which has 38 protons, 96 protons and neutrons, plus barium again, which of course has 56 and 141, just like above, plus the 3 neutrons again. So we've got 3 neutrons plus energy again. And the reason for that is if you were to weigh the plutonium and the neutron, you would find that it would be just slightly heavier than the strontium atom, the barium atom, and the 3 neutrons. That mass deficit has been converted into energy according to Einstein's famous equation, E equals mc squared. Now these processes, of course, can be used in nuclear reactors to produce energy, to produce electricity. The basis of a nuclear reactor is this. You have a container in which you have some fuel rods. Now these might be uranium or they might be plutonium. But the idea is that this is the kind of formula that's going to apply. Neutrons are going to be striking the rods, and that is going to produce decaying atoms, or the atoms that result from the decay of the uranium, so strontium and barium, but 3 more neutrons and energy, and those 3 more neutrons will hit the plutonium in this case again and produce yet more energy. So this is producing energy in the form of heat. So you surround this with water, or you can use carbon dioxide, and what you have is you have a tube which takes the water out. There should be a gap here obviously to let the water out, and into another container where the steam can be allowed out to drive the generator, or it turns the turbine which turns the generator. Let me just draw that up so you can see the whole thing. So essentially we're taking this very hot water out. The steam from the hot water rises and turns the turbine, which causes the generator to turn. That's the principle we covered when we did generators. And then of course you need to bring the now slightly cooler water back into the reactor. There needs to be an inlet pipe there so that the water can be heated up again by the energy that's coming out of this reaction in the form of heat. Now, if that were all, then very quickly the reactor would blow up, because this is a chain reaction. This is just going to get more and more and more aggressive, producing more and more and more heat. And so you have rods, which are not fuel rods. These are probably made out of something like boron, which can be raised and lowered between the uranium rods. And what they do is they absorb the neutrons. So you're producing neutrons, which would, if you didn't do anything about it, just hit other plutonium or uranium fuel rods and create yet more energy. But what you do is you absorb some of these neutrons so that you haven't got quite so many, and that way you can control the amount of heat that is being produced so that you don't get too dangerous a situation. As I say, the material in here might be water. Sometimes it's carbon dioxide, so you've got very hot carbon dioxide being pumped around in order to drive the turbine which turns the generator. So what are the issues associated with the use of nuclear reactors? Well, we are using slow-moving neutrons which split essentially the uranium or the plutonium atoms, producing smaller atoms. They also produce 3 more neutrons, each of which can then split another uranium or plutonium atom. This produces a chain reaction, because you start with 1 neutron, it produces 3, each of those produce 3, each of those produce 3, and so on. Very quickly you've got a huge reaction, huge amount of energy. That's the basis of a bomb. So you have to regulate the amount of energy produced by the use of the control rods. You get waste products which are radioactive, and the reason they're radioactive is that the atoms have too many neutrons, so they're unstable, so they too need to decay. But in essence what you're doing is splitting the nucleus, and in doing so you create a mass deficit, and that produces energy. There's a big risk, which is the risk of radiation leaks, such as was the case many years ago in a reactor in Chernobyl. You may have heard of this. There was a major radiation leak around Chernobyl, and that obviously is very, very dangerous because you've got radioactivity in the area. You've also got the problem of the disposal of the waste, which sometimes has a very long half-life, so it will be radioactive for thousands of years. And then at the end of the life of the power plant, you've got the problem of decommissioning it. That power plant is heavily radioactive, particularly the section where the uranium was, and so it may take many years and cost a great deal of money to decommission it. So let's now consider the advantages of nuclear power stations compared with, say, coal or oil power stations which use fossil fuel. Well, firstly, you're going to produce lots of energy. These reactions produce a huge amount of energy as the atoms are split. There's no CO2, no carbon dioxide, no greenhouse gases. The fuel is actually relatively cheap when you compare it with other fuels which often have to be mined. You actually use relatively little fuel because there are billions and billions of atoms, and when you split some of them you get a lot of energy. And there's a relatively plentiful supply of the uranium that you need. But now let's look at some of the disadvantages that have to be taken into account. It's very expensive to build the power station because it has to be absolutely safe. The waste products that are produced are radioactive, so storage and disposal is going to be a problem. There will always be the risk of leaks and a major disaster in the area where the power station is sited. When the power station comes to the end of its life, there will be a heavy decommissioning cost, and it will probably take many years for that power station to be dismantled. Uranium is in fact a non-renewable source. You can't actually make uranium, but on the positive side, some of the waste products can be partly reprocessed for reuse. But of course, perhaps the biggest disadvantage of all is that the material can be used to make bombs, so you are always vulnerable to having that material stolen, particularly by terrorist groups. So security is a key issue.